This is the first video for Notes D. Notes D focuses on electron arrangements, electron configurations, and in part one we're going to talk about the trend in ionization energy that led us to understand these electron arrangements. So although you may have discussed ionization energy in prior classes, this is a very specific definition for the first ionization energy, meaning it is the energy to require the very first electron of the atom to be removed. We are always removing electrons. Yes, ions are formed by gaining electrons, but that has nothing to do with the trend in ionization energy. So when you define ionization energy, it is always removing an electron. There's a very, very important stipulation that you have to remember, and that is that the atom must be in a gaseous state. It has to be in the gas phase. And that is because only in the gas phase have you essentially eliminated all of your intermolecular forces. So you've got to be comparing just the ionization energy of pulling that electron out, considering only the attraction between the atom itself. We don't want to be considering the attractions of other forces, exterior forces. So intermolecular forces would be the forces between an atom and another atom. We want to be looking only at the forces within this first atom and how much energy it takes to pry that electron off. So there are some common trends in the first ionization energy of the atoms as you go across the periodic table or as you go down a column on the periodic table. So as you go across the periodic table from left to right, you have more and more protons in the nucleus, more pull on those electrons. So it gets harder and harder to remove those electrons. So you see the elements at the right having the highest ionization energy. As you go down a column, you're getting further and further from the nucleus. So it's actually at the top of the column where you would have the highest ionization energy, because those electrons are very close to the nucleus. This is a graph of first ionization energies for the atoms on the periodic table, meaning it is how much energy it takes to remove the very first electron, only one electron, being removed from the atom in the gaseous state. Let's take a look at some of the peaks on this graph. Helium, neon, argon. These are our noble gases. These are things that are the furthest on the right on the periodic table. So as we just discussed, if it's the furthest to the right, it's going to have the most protons in its group across. So when we see those peaks, we can tell from those rows on the periodic table that those elements would have the highest amount of ionization energy from that set. Now let's look at this graph in the way that it relates to the rows of the periodic table. So I have each row of the periodic table highlighted in a specific color. So if you see the first row in the periodic table, which is just helium and hydrogen, you see they're in green here, and that's going to be going from left to right. Where helium is on the right, with more protons, it's going to be the peak of that row. If you look at the second row across, we would start with lithium and go over to neon. So you see lithium at the bottom with the least protons and neon at the top with the most protons. Whereas if you look at the third group, you're going to see the same thing. You see sodium on the left going up to argon on the right. So sodium's at the bottom of its group, argon at the top of this group, representing the third row. The fourth row goes from potassium to krypton. This is going all the way across the periodic table. You're going to have your D block now, so you see a little bit more dots representing more atoms in that fourth row across the periodic table. Then you have your fifth row, your sixth row, and your seventh row. So for each row across the periodic table, you see your alkali metals at the bottom, the left of the periodic table having the least number of protons, and your neon gases at the top, representing all the way to the right, how they have the most protons and so the most pull. That's going to make it require the most amount of energy to remove an electron. Next, I want to look really closely at some of the trends within the first two rows in the periodic table. And I want to tie this to their specific electron configurations. because the way that we determined electron configurations was from the trends in ionization energies. So what is it that these configurations do to the stability of an atom? How does the amount of energy required to remove an electron tell us about what the atom is arranged like inside? So let's use neon as our first example. If I were to write out the electron configuration for neon, it would be 1s2, 2s2, 2p6. Whatever electron I remove would be in the valence shell. We'd be coming from the 2p6. On the other hand, if I look at helium, the electron configuration for helium is 1s2 only. So if I'm going to remove an electron from helium, I would be stealing it from the 1s orbital instead of the 2p orbital. You're always removing the very last electron. So what that means is the amount of energy it takes to remove that electron is driven by the location, the orbital, in which you are stealing the electron from. It requires more energy to steal from the 1s orbital than it does to steal from the 2p orbital, because helium's ionization energy is higher than neon's ionization energy. The next thing that I want to focus on here is the small dips that occur as you go across a row on the periodic table. This has to do with the stability of an atom. If it requires more energy to remove an electron, for example, helium requiring more energy than neon, that means that helium's electron configuration was more stable than neon's electron configuration. There was more traction between the 1s orbital and the nucleus than there was between the 2p orbital and the nucleus. So why is it that as you go across the periodic table, you have some points along the way that seem to be more stable than their next point? Why are some higher than others? The most important concept to know here is that if something is more stable, you will get a peak. Whether it's a small peak or a big peak, stability will lead to a peak in this graph. So what are some of the most stable atoms that we know of? Of course, are noble gases. We've always learned that the noble gases are inert. They do not react with other substances because they already have a completely full valence shell. So the valence shell for neon would be 2s and 2p. The second principal quantum number is full. We have 8 total electrons, 2 in the s and 6 in the p, so neon is completely full. The octet rule actually says that atoms want to be stable, like the electron configuration of the noble gases. So yes, these are the most stable, but as it turns out, anything that actually completes a shell, maybe not the entire second energy level, but maybe just completing the 2s shell, will lead to a peak, which is why you see beryllium having a higher ionization energy than boron. The peak between nitrogen and oxygen is a little bit harder to explain because it seems to come in the middle of the p orbital. But if you think about the orbital diagram for a p orbital, it would have 3 orbitals. And if we were only having 2p3, such as for nitrogen, you would fill 1 arrow in each of the orbitals. If you were doing it for oxygen, that would be 2p4. Again, you have 3 orbitals. You spread them out, but then you're going to come back and pair 1. There's a super stability that occurs when the electrons are what we call paramagnetic, perfectly parallel in the 2p3 configuration. So that is why oxygen is actually down below the nitrogen. Nitrogen has a small advantage in stability because it has perfectly paramagnetic electrons in the 2p orbital. So you need to know this graph inside and out. You need to be able to explain the peaks at the top and the dips, the peaks that occur below, and the pseudo-stability that occurs within the electron configuration, and tie this all together. You need to know this so well for the first 20 atoms that you could draw this for yourself with an annotated direction. So here is more of a simplified version of this graph that you should be able to draw at least this much for yourself. So it starts with the first group, our first row across the periodic table, I should say. This would be your hydrogen and helium. And then when we start down here, this L is actually lithium, goes all the way up to neon. You need to know that in between your S and your P orbital, you drop, and where you're at P3 to P4, it drops all the way up to neon. And then when you start over with sodium, as you go through your 3s orbital, then you see a drop. Then you half fill your p orbitals, see another drop. Then you completely fill 3p6 up to argon, and then drop back to 4s1, 4s2. And that'll take you through the first 20 atoms. You need to be able to draw this, including the drops. And you also need to be able to explain the drops and the peaks specifically. This is kind of a weird little table down here. You don't necessarily need to know the letters for the shells. It is a labeling system that they use, especially when you're talking about ground and excited states and stuff like that. Your first energy level would be your 1s, which can hold 2 electrons. Your second energy level includes 2s and 2p, which includes 8 electrons. Sorry, this is shifted a little bit. There we go. And then your third energy level would hold 8 because you only have 3s and 3p. Right here is you're going from sodium to argon since you're only doing the first 20 atoms. But you know that there's also a 3d, which is where 18 electrons would come in. And you're not going to have to necessarily explain 3D, but I would expect you to be able to apply the idea. Like if I asked you, where would you see a dip in the d orbital? Well, knowing that it has to do with being perfectly paramagnetic, you should be able to deduce that if there's 10 electrons, that having exactly half of that 5, having each of the 5 orbitals in d to be completely full, that paramagnetic would be more stable, and so you would see a drop between d5 and d6. So as complicated as all of that was, we were only focusing on the first ionization energy of each atom. Now we're going to move on to look at the second ionization and then what they call subsequent ionization energies. So this is going to be the second ionization energy is going to be how much to remove the second electron. And yes, it still also has to be in a gas. So still removing gas, but now we're looking at the second electron. So you already have 1 electron removed when you start, and then you remove another electron, giving a 2+ charge to the atom. So the second energy is the energy required to remove only that second electron. It does not include the first ionization energy. These would be measured as 2 separate energies. So if you end up with a 2+ atom, you have both the first ionization energy and the second ionization energy required to reach that cation status. So this is a good example of successive ionization energies or subsequent ionization energies for potassium as an example. So you see the electron configuration for potassium up at the top, 1s2, 2s2, 2p6, 3s2, 3p6, and then ending with 4s1. So 4, being the highest principal energy level, would be our valence shell. So an electron in the valence shell requires only 419 kilojoules per mole of potassium to remove. Once I reach into the third energy level, which would then be stable, would have 8 valence electrons. Notice this huge jump going from 400 to 3,000 kilojoules per mole. The subsequent energies do require more. There's an increase, but there's no huge jumps like there is between the 419 and the 3000. So your goal, if you're looking at data like this, is to find the huge jump, and that's going to tell you where your valence shell was. This first electron came from the valence shell as it required very little energy, whereas the others required much more energy as they're going from a more stable shell, the third energy level. So we're going to look at one more graph. This graph is very different because it will show how to remove all of the electrons from a single atom. This is different from the graph that we looked at before, which showed how to remove only 1 electron from each atom. and how much energy that would take to remove the first electron from different atoms. Now we're looking at only one atom, potassium for this example, but we're going to remove all the electrons. It's just that we're going to do that one by one. So to make a graph of successive ionization energies, you have to tie this to the electron configuration again. Wherever the valence shell is, so that would be my 4s for potassium, that's going to be their very first electron to be removed. If this is the valence shell, now you want to show a big jump. So you see how that's the largest jump. There are other jumps up here, but that's the largest jump. You want to indicate that that is the valence shell. If I wanted to remove more electrons from that potassium, the next shell I would dip into would be the third energy level, which contains 8 electrons in both 3s and 3p. So that's going to be this row here. You do want to make sure that you show exactly 8 electrons in this third energy level. However, there actually is not a substantial difference between removing from your 3s2 versus your 3p1 or 3p6 versus 3p4. So you don't see the small dips that you were able to see in the previous graph, because these are at the same energy level within the same atom with the same number of protons. You do not get a substantial dip here. So there's actually no evidence for sublevels in this graph. And that's an important question that comes up on IB. Does this graph show evidence of sublevels? This graph does not. The graph of first ionization energies for the first 20 atoms did. So let's keep going. Say we've removed now all of the electrons from the fourth and third energy levels. Now we're going to go into the second energy level. So again, I'm going to show all 8 electrons there. No evidence of sublevels, but you are going to show an increase between the second and third energy levels, because you are now closer to the nucleus as you go into the second energy level. You are going to be able to see a noticeable increase. It should, however, be smaller than the increase in your valence shell. That's really important. Okay, and then let's finish this off. Say we've removed everything from the second energy level. The last 2 electrons standing would come from the 1s, being held the closest to the nucleus. That's going to be the highest ionization energies. And again, you are going to show an increase as you go from your second energy level to your first energy level. That should be similar to the increase when you went from the third energy level to the second energy level. And again, both of those being smaller than the increase from the valence electrons. So to summarize, it does increase generally over as you're increasing the number of electrons that you're removing. It does require more and more energy as you're removing them closer and closer to the nucleus. You want to make sure that you have a very big, large jump to show where your valence electrons are. You do want to show the number of electrons in each energy level, but do not increase for sublevels. That is only in the graph that we went over in the beginning, where you were going through the first 20 atoms' first ionization energies.